In this lecture, we will derive the formulas for the coefficients of the trigonometric Fourier series for a continuous function that is defined on a closed interval from -L to L. The trigonometric Fourier series is given by the summation from n equals 0 to infinity of a sub n times cosine n pi x over L plus b sub n times sine of n pi x over L. Writing out the Fourier series, we get a sub 0 times cosine 0 plus a sub 1 times cosine pi x over L plus a sub 2 times cosine 2 pi x over L and so on, plus b sub 0 sine 0 plus b sub 1 sine pi x over L plus b sub 2 sine 2 pi x over L and so on. Cosine 0 is equal to 1, and so the lead term of the Fourier series is in fact a sub 0. On the other hand, sine 0 is equal to 0, and so we really do not have a b sub 0 term in the Fourier series. For this derivation for the coefficients a sub n and b sub n, and this is a standard derivation, we make some assumptions about the Fourier series. One assumption that we make, and this is a very crucial assumption, we assume that the Fourier series is uniformly and absolutely convergent. With this assumption, we can carry out term-by-term integration of the Fourier series. Suppose that f of x is equal to its Fourier series on the closed interval. We multiply both sides by cosine m pi x over L. Because we assume the Fourier series to be uniformly and absolutely convergent, we can carry out term-by-term multiplication by cosine m pi x over L to the Fourier series. We can also carry out term-by-term integration, and so if we integrate both sides of the equation, the left side is the integral from -L to L of f of x times cosine m pi x over L. For the right side, we have the integral from -L to L of the Fourier series, where each term in the Fourier series is multiplied by cosine m pi x over L. With term-by-term integration, we will be integrating products of cosines. This includes the a sub 0 term. We will also be integrating products of sine and cosine. If m is equal to n, then cosine m pi x over L times cosine n pi x over L equals cosine squared n pi x over L. This is now an elementary integration exercise where we use the half-angle formula. Cosine squared n pi x over L is equal to 1 plus cosine 2 n pi x over L all over 2. The integral of 1/2 over the interval from -L to L is equal to L. An antiderivative of cosine 2 n pi x over L is equal to L over 2 n pi times sine of 2 n pi x over L. Replacing x by -L or L, we get sine of plus or minus 2 n pi, which is 0 since n is an integer. And so when m is equal to n, the integral of cosine m pi x over L times cosine n pi x over L is equal to L. Now suppose this time that m is not equal to n. We apply the trigonometric identity that the product of cosine m pi x over L and cosine n pi x over L equals half the quantity cosine the quantity m pi x over L plus n pi x over L plus cosine of the quantity m pi x over L minus n pi x over L. An antiderivative of the first term is equal to L divided by the product of m plus n and pi times sine of the quantity m plus n times pi times x all over L. An antiderivative of the second term is L divided by the product of m minus n and pi times sine of the quantity m minus n times pi times x over L. Because m is different from n, there is no danger of this fraction becoming undefined. And since m and n are both positive, this fraction is also a real number. Plugging in plus or minus L, we get integer multiples of pi for the angles, so that we get zeros out of the sine functions. And so the integral of the product of cosine m pi x over L and cosine n pi x over L on the interval from minus L to L is 0 if m is not equal to n. We use another trigonometric identity for the product of sine and cosine. The integrand is equal to half the quantity of sine of the angle n pi x over L plus m pi x over L and then we have the sine of the angle n pi x over L minus m pi x over L. We leave it as an exercise for the viewer to check that the integral of this quantity from minus L to L is equal to 0. To write down the formula for a sub n, we will first deal with the case when n is not equal to 0. And so we will set aside poor little a sub 0 in the meantime. Because of these two equations, the only term that we have to pay attention to on the right side of this integral equation is when we have the product of cosines and when m is equal to n. Likewise, the left side should have the integrand f of x times cosine n pi x over L. Upon integrating from minus L to L, each term in the integrand on the right side, where the subscript of a is not the same as m, vanishes. And so for positive values of n, the integral from minus L to L of f of x times cosine n pi x over L equals the integral from minus L to L of a sub n times the square of cosine n pi x over L. The integral from minus L to L of the square of cosine n pi x over L equals L. And so the integral from minus L to L of f of x times cosine n pi x over L equals a sub n times L, for n not equal to 0. And so we have the formula for a sub n for n equals 1, 2, and so on. Now let's go back to the a sub 0 term before we completely forget about it. We get a non-zero integral out of a sub 0 times cosine m pi x over L only if m is equal to n. For a sub 0, n is equal to 0. And so m must be equal to 0 on the right side. M must also be equal to 0 on the left side. Cosine 0 is equal to 1, and so on the right side we are integrating a sub 0 from minus L to L. This gives us a sub 0 times 2L. Cosine 0 is still equal to 1 regardless of the side it's coming from. And so on the left side we have the integral from minus L to L of f of x. And so we have the formula for a sub 0. For deriving the formula for the b sub n's, instead of multiplying by cosine m pi x over L, which we did when we derived the formulas for the a sub n's, this time we multiply by sine m pi x over L. Each a sub n is now attached to a product of sine and cosine. But upon integrating from minus L to L, the product of sine and cosine disappears, so that the a sub n terms disappear when we integrate from minus L to L. And so now we have to deal with the products of sines. This integral is similar to the integral involving the product of cosines. We leave it as an exercise for the viewer to check that the value of the integral is equal to L when m equals n, and it is equal to 0 when m is different from n. The result is that the integral from minus L to L of f of x times sine of n pi x over L is equal to b sub n times L if n is not equal to 0. Consequently, b sub n is equal to 1 over L times the integral from minus L over L of f of x times sine of n pi x over L for n equals 1, 2, and so on.